Hi, I'm Randall Heyman, a mathematics academic, and this is my Corona Help playlist. If you'd like me to make a video for your class, your child, your grandchild, or you yourself, then just comment below and I'll see what I can do. Okay, we're clocking through the different steps in showing that any integral domain can be embedded in a quotient field. This is part 3, and this video involves step 2, where we define the two binary operations for fractions. So you can see here, this field that we're developing, we can consider it a specific case is fractions. So I'm tending to make this concrete by referring to the integral domain as integers and the quotient field as fractions. So where we've got to is we've got a set S that consists of the ordered, well, what's this? Well, in the middle, we've got the ordered pair AB. So that's just a pair of numbers in a particular order. I've put these square brackets around because it's actually the equivalence class. And this gets around this problem that 3 on 2 is the same as 6 on 4. So have a look at the previous video. So that's part 2 if you've got problems with that. And the conditions are that, well, A and B are integers, and B does not equal 0. Now, if there's one thing that's come through a lot with all these abstract algebra videos that I've done, is that to create something like an integral domain or a field or a ring or a group, you need a set and you need two operations. We've got the set, so now we want to talk about going the whole hog and adding plus and multiplication. So let's talk about let's do addition first, which is the harder one, of course. So if we've got 3 on 2 and we want to add 5 on 7, well, we know what we do is we take 3 times 7 plus 5 times 2 and we divide by 7 times 2. So what that's how we would present it in school. But what we do here is that we say that A, B, so we take the asset class containing AB, in this case 3, 2, so this would just be 3 and 2, plus C and D, and what does it equal? It equals AD, the top bit is AD plus BC and the bottom is BD. Okay, and for multiplication, what have we got? We've got, say we had 3 on 2 times 5 on 7. Well, then we just multiply 3 times 5 and 2 times 7. So once again, we can now construct what that means. That means that A, B. So our rule for multiplication is if we've got the equivalence class containing the ordered pair AB and we multiply it by another element of S, which we'll call CD, we'll call this containing CD, then that will give us the equivalence class AC, DD. Actually, I don't like that. The brackets are a bit close. So I'll try and maybe write a little bit bigger. Okay, now, I don't want to go into too much detail now because we've basically done what we need to do, but there's a few things to point out here. The first is this a valid, say, addition or multiplication? Let's just look at multiplication, but it's the same argument for addition. So if we go back and look at S, well, yeah, let's go back to S. Just got it there. Okay, let's just go up. I want to point out this thing here. This is important. B cannot equal 0. So the second thing cannot equal 0. So here we've got, here B equals 0. Sorry, does not equal 0. and D does not equal 0. So, since let's write it this way. So BD does not equal. See, we've got BD here and here. It's important that these are not 0, otherwise the whole thing unwinds. Because if these are 0, then this is not in S. This is not in S, and it has to stay in S. We can't have these fractions and then you're adding and multiplying fractions. You can use things that have got nothing to do with fractions. So BD equals 0. Now here there's a subtle point. I'm not going to write it up, but when we say that BD is not equal to 0, this is where we get to that no zero divisors, which we saw are a very important part of integral domains and also fields. So the fact that we don't have any zero divisors means that that this all works really well. I probably haven't explained that. If anyone's interested, I'll have another think about that, maybe explain that better. Now, the next thing that we have to do, which I don't think I want to actually labour, because it's quite a lot of detail, but it's just important to know in passing this, and that is, it's important that we don't lose, that it's important that this works when we've got these equivalence classes involved. It's really important that if we go, that here, if we put, well, 3 on 2 is an element of this equivalence class, and so 6 on 4. And here we've got 5 on 7, and we've also got 10 on 14. It's important that if we pick any element of this equivalence class and add it to any element of this equivalence class, that we'll get this equivalence class. So that's the next thing that you'll see if you look at Freilich or in that PDF that I've put below the previous video. So you might say that's just sort of checking that the addition and multiplication are well defined. I think I might just skim over those two things. I've sort of explained it. If people need more details, they can ask me. So that's so that's the second step. So in the third step, we'll just be checking that in fact this set S with, the set S, well, actually, this is wrong what I've put up here, actually. The set was S, and we've added addition and multiplication. So I suppose where we've now got to is that the set of fractions, well, this is what we're proposing it for it to be, and I'll put a question mark there because we've still got a couple of steps to go to really finish this off. Any questions on this or anything else in mathematics at any level, virtually any level? Put a comment below or send me an email.